the now magnetic monopole rule. That's what we'll be discussing in this section. So consider an ordinary magnet. Now we know that a magnet has two poles, a north pole and a south pole, and we can draw the field lines of the magnets to get something that looks like the one on the screen. Now, we know that the field lines flow into the south pole, and the field lines flow out of the north pole. But what happens if we just have a magnet with one pole? In other words, could these types of magnets exist? Well, to truly understand that, we must define what a monopole is. Well, as the name suggests, a monopole is just one pole, where mono means one and pole is just self-explanatory. So these types of magnets are examples of magnetic monopoles. Now, what does the no magnetic monopole rule state? Well, it simply states that magnetic monopoles cannot exist in nature. That's precisely what the no magnetic monopole rule states. But in the future, a group of scientists could come together to experimentally develop a magnetic monopole or find one in some area of nature. So therefore, magnetic monopoles could exist, but we just don't know of any, or we just haven't created any. So in essence, right now, we presume that magnetic monopoles do not exist, and that's what the no magnetic monopole rule simply states. But can we encode this into mathematics? Well, of course we can. Namely, we can encode it as the divergence of the magnetic field is equivalent to zero, and this is one of Maxwell's equations. One of the most significant equations in all of electrostatics is Coulomb's law, and that's what we'll be discussing in this section. So let's begin without further ado. Now, let's start by defining electrostatics. Electrostatics can be thought of as the branch of electromagnetism that deals with charged particles that are stationary, or in other words, have a velocity of zero. Now, thanks to the book Feynman Lectures on Physics, Volume 2, for all the information and formulas used throughout this section. Okay, so let's start by writing down Coulomb's law, and then by decoding it. Coulomb's law can be written as such. Namely, it can be written as F1 is equivalent to 1 over 4 pi epsilon naught times Q1 times Q2 over R squared times E1, 2. This is Coulomb's law, and this is also equivalent to negative F2. But before we proceed forward, we need to make 2 points clear. Number one, we need to make sure that F1 is a vector and E12 is a vector, and they are vectors. Now, you might see R to be the magnitude of another vector, also called R with some subscripts. But in this section, for simplicity, we're just considering R to be a scalar. So it's not a vector, it's not a magnitude of any vector, it's just a scalar. Okay. And we can also say that F2 is going to be a vector, or in this case, negative F2. So now that we've defined what's a vector and what's not a vector, let's come to the second point. The second point is the fact that we can ignore this negative F2 for now. We'll bring it back up a little bit later, but for now we can ignore it, because that just makes everything a little bit more complicated. So over here we have Coulomb's law, and although it may seem daunting, it's actually pretty intuitive. But to understand the intuition behind Coulomb's law, we must draw a diagram. So consider these two charged particles, particle 1 and particle 2. Particle 1 has a charge of Q1, and particle 2 has a charge of Q2. We can draw the distance between these particles as R. So we have particle 1, particle 2, Q1 and Q2, and the distance is R. So this is our basic setup. So now that we've talked about this, and we've talked about this equation, we could just end this video. But we have to talk about the relation together. So F1, we label everything, is going to be the force. But what is the subscript? Well, the position of the subscript corresponds to on. In other words, if this was 3, then we would have the force on 3, or the force on charged particle 3. Right now it's 1, so we're considering the force on charged particle 1. Now over here, we can group this whole thing to be a constant, often abbreviated as K. Now, as we just discussed earlier, Q1 and Q2 are the charges, R is the distance, and E12 is a unit vector. But what's the purpose of these subscripts? Well, similar to F1, these positions correspond to to and to from. In other words, this unit vector is pointing to charge particle 1 from charge particle 2. That's what this is saying right here. So the position in which 1 is occupied right now is 2, and the position in which 2 is occupied right now is from. Okay, so now that we have talked about that, let's now talk about the significance of E12. But to understand the significance of E12, we must talk about the universal law of gravitation. The universal law of gravitation is F is equivalent to G times m1 times m2 all over r squared. And Coulomb's law is F is equivalent to K times Q1 times Q2 all over r squared times E12. So Coulomb's law and the universal law of gravitation. Now they pose some striking similarities because they have a constant, g, k. We have mass 1, mass 2, we have charge 1, charge 2. We have the distance, distance squared, and the distance, distance squared, and then we have a unit vector. Now this representation of the universal law of gravitation, we don't have a vector. Okay, so as you can see, these two equations resemble a striking similarity. But there's also another important point we need to touch on, namely the fact that gravity is just an attractive force. If we have two objects and we're considering gravitational force, we know that they'll attract each other, or it's an attractive force. But electromagnetism is an attractive force, but also a repulsive force. Because likes repel and opposites attract. Basic elementary school physics. So we have attractive, repulsive, and we just have attractive over here. So this equation needs to distinguish between an attractive force and a repulsive force. So where do we find that in Coulomb's law? And although it may seem subtle, and yes, it does deal with the signs of Q1 and Q2, it actually is really crucial to have E12 in this scenario. Okay, so let's illustrate that right now. The reason why E12 is there, and how it can just make things way better. Now, I ignore the subscript over here, but this is F1. Okay. So, let's redraw the whole diagram on a bigger scale. So, simply, we just have this. We have particle 1, particle 2, we have R, we have Q1, we have Q2. Okay, so we have this set up over here, and let's write Coulomb's law down. So we have F is equivalent to F1 is equivalent to K times Q1 times Q2 over R squared times E12. So let's say that we have two cases. Case number 1. Let's say that Q1 and Q2 are both positive. So if they both are positive, we find that the coefficient over here, the coefficient of E12, is going to be positive. So therefore, E12 points in the same direction it originally points in. E12 is 2, 1 from 2, which means that it points 2, 1 from 2. So we have E12 looking like this. That's how E12 looks like. Now, for the purposes of this setup, ignore where E12 is placed. Just imagine, or just focus on its direction, because that's what we're analyzing right now. Now, we see that this case is symmetrical. Symmetrical in the sense that we can also use the same case to say that Q1 and Q2 are negative. Why can we do that? Well, in fact, we can do that without any prior knowledge. The reason is because Q1 and Q2 are multiplied together. Positive times positive is positive, and negative times negative is, well, positive. So we can make Q1 and Q2 positive or Q1 and Q2 negative. So therefore, E12 points in the same direction it originally points. Well, if we consider this whole thing just to be another big constant we'll call C, we'll just have F1 is equivalent to C times E12, right? And if it's C times E12, well then that just means F1 points in the same direction as E12 since C is positive, and secondly, it's just E12 scaled as C. C1, E12, or F1. So this is the force right here. And as you can see, it points right here. It's scaled by C, and it points in the direction of E12, since C is positive. Okay, so we just got that right now, and we just analyzed case 1, and we see that it makes sense. If both of these are positive, then they must repel each other. So 1 should go like this, and 2 should go like that. But let's now consider a second case. Case number 2. Well, what is case number 2? Well, case number 2, well, let's try this first. Q1, Q2 over R squared times E12. Case number 2 is when Q1 is positive and Q2 is negative. So this implies positive, this implies negative, plus minus. Now, this case is also symmetrical in the fact that we can also consider Q1 to be negative and Q2 to be positive. The reason is because they're multiplied. Positive times negative is negative, and negative times positive is also negative. So, therefore, we have symmetry over here. So, plus minus, so we'll consider the first part in case 2. So, plus minus, and we know that this whole bulk is now negative. So it's negative. So we'll call this negative C, since it now has a negative sign. So we have F is equivalent to E12, which is equivalent to, well, F1 is equivalent to E12 times this negative C. So that's what we have over here. So we have this coefficient, which is negative, then we have E12, and this is equivalent to negative C times E12, right? So that's what we have right here. And this seems pretty obvious. But here's where the crucial part, or the crucial significance of E12 comes in. So we can just move the negative over here. Now don't consider this as C minus E12, consider this as C times negative E12. We can write it like this, where C is the scaling factor, and we have negative E12. Well, what's negative E12? Well, negative E12 points in the opposite direction from E12. So, we can write it like this. Negative E12. Obviously it looks bigger, but right now from the limitations of the whiteboard, we have a negative E12 over here. So now that we have negative E12, we see that F1 is just a scaling of C times negative E12. So in this case now, or we'll actually put both of these in purple so you can see the significance. So we have negative E12. We have F1, which is scaled as C, and then points in the direction of negative E12, makes F1 look like this. And now it points inwards. So as you can see, this makes logical sense from our prior knowledge in elementary school physics that namely likes repel and opposites attract, because we see that 1 should be pointing like this, and 2 should be pointing like this. Therefore, they attract. But we just talked about 1 right now. We haven't really talked about 2 over here. So what is 2? Because if we talk about 2, then only can we understand whether this E12 actually works. because what if 2 all points in this direction and not this? Well, that's where we bring up the negative F2 that we talked about. This negative F2 actually portrays a symmetry. It portrays a deep symmetry. Namely, it portrays an equal and opposite reaction to F1. So if F1 points in, let's say, in the black direction, then negative F2 is going to have the same magnitude as F1, but just pointing in the opposite direction. So this will be F2. Now you might be thinking this is negative F2, right? Well, F1 is equivalent to negative F2. Therefore, F2 is equivalent to negative F1. And how would F1 look if it was negative? Well, it would point the opposite way. It would point like this. So therefore, we have F2 over there. So now that we've immediately identified F1 and F2, we do the same thing with the other case, or case 2. So in the purple case, we find, what is F2? Well, F2 is negative F1. If it's negative F1, it points in the opposite direction as F1 with the same magnitude. So this is F2. Now, by the way, this might look small, but that's because of the limitation of the whiteboard. F2 over here in black still has the same magnitude as this F1. So from Coulomb's law, we've just seen that this unit vector, although it might seem just like a small piece of information, not really crucial, it helps us show the attractive part of the electromagnetic force and the repulsive part of the electromagnetic force. And that is actually really crucial. So instead of just plugging and chugging, in essence, just plugging and chugging the constants into Coulomb's law, we now understand how it plays a bigger role. We talked about each of these things. We've talked about Q1, Q2, R squared. We've talked about how it's an inverse square law. And it is indeed an inverse square law. The reason is because we have, let's say, 2 particles over here and we increase the distance. Well, then the distance, as the distance increases, the force will decay really quickly. And that's shown by the R squared factor in the denominator. We call those types of laws inverse square laws. Now that name is usually reserved for the universal law of gravitation, but we can also consider that to be, we can also consider inverse square law to be Coulomb's law in this case right now, because we're just dealing with Coulomb's law. So in essence, what it just states is as the distance increases, the force between them decays quickly. Okay, so now that we've talked about that, we can make this section to an end. The Lorentz force law, that's what we'll be discussing in this section. So you may be wondering who created the Lorentz force law? Well, that's none other than Lorentz himself. Okay, so let's consider the equation for the Lorentz force law. Now, one specialty of this equation is that it doesn't involve any constants. In other words, it doesn't involve epsilon naught, e, pi, or even 1. So that makes this equation quite special. Now, in order to build an intuition for this equation, let's start by labeling it. F is equivalent to the force, Q represents the charge, E represents the electric field, V represents the velocity, the big X represents the cross product, and B represents the magnetic field. Okay, now let's draw some conclusions based on some observations. So observation number 1. Let V equal to 0. Then F is equivalent to Q times E. Now this is pretty simple. If we set V equal to 0, we find that F is equivalent to Q open parentheses E plus 0 cross B end parentheses. 0 cross B is just 0. Adding that to E just gives us E, and we get F is equivalent to Q times E. But the specialty comes from the fact that if we set E to be the Coulomb field and multiply that to Q, we just get Coulomb's law back. So in essence, we've just derived Coulomb's law from the Lorentz force law. Observation number 2. If we still set V equal to 0, we find that we have no magnetic contribution. Or in other words, the magnetic field has no effect on a stationary charged particle. And this is another important fact in magnetostatics. So now that we've talked about these two observations and conclusions, it's important to touch upon one more point. namely the fact that these two statements could have either come before or after the creation of the Lorentz force law. Yet it doesn't really matter. What matters is the fact that from the standpoint that we're looking at the Lorentz force law from the first time, we can derive these conclusions. In the previous section, we talked about Coulomb's law, which is one of the most significant tools in all of electrostatics. Now in this section, we'll introduce the principle of superposition as well as the electric field. So let's begin without further ado. Okay, now thanks to the book Feynman Lectures on Physics, Volume 2, for all the information and formulas used throughout this section. So let's draw a diagram to truly understand the principle of superposition. Now you've probably been accustomed to this diagram because of the countless amount of times we've talked about it in the previous section on Coulomb's law. Now this is the diagram, and we know that if we have particle 1 and we've gone to consider the force on particle 1 because of particle 2, we can use Coulomb's law. And if we want to consider the force on particle 2 because of particle 1, we can also use Coulomb's law. So we might feel pretty successful right here, because a lot of physics is dealing with forces, but we have to consider the two conditions imposed on this model. Number 1, we're considering a two-particle system. And number 2, all particles are stationary. So these are the two conditions. Number 1, we have a two-particle system, and number 2, all particles are stationary. But before we talk about how we can alter one of these conditions, let's talk about why it's actually pretty useful to have some sort of model like this. Now you may be thinking that this is a highly oversimplified or highly unrealistic model, and practically it is. But a lot of times in science and physics, we start with highly unrealistic or maybe just oversimplified models, and then progress outward to encompass a lot of phenomena. And this is actually more oversimplified than realistic, because it's actually very crucial to understand these types of systems in order to gain a better understanding of the world around us. Okay, so let's alter one of these conditions. So let's keep this condition in place, that all particles are stationary. But let's remove this 2, and let's consider a 3-particle system. Now the question is, can we do that? Can we use the existing mathematics, the existing observations, the existing discoveries that we have to describe a 3-particle system? Well, let's find out. Now Coulomb's law is especially designed to consider 2 particles, because we have the distance from one particle to another, we have the force on one particle, so it's practically designed to consider 2 particles. So if we have a 3rd particle in here, we don't have a Coulomb's law that considers 2 particles just in one equation. It's not bundled up that way, or it's not created that way. So we have a problem, or do we? The question is, how do we overcome this situation? Is there something, or an experimental fact, or a theoretical fact that we can exploit or use in order to find the force on particle 1 because of particle 2 and particle 3? Well, of course we can do that. Namely, through the principle of superposition. Now, it's important not to confuse this with quantum superposition. But what does the principle of superposition tell us? Well, let's consider this 3-particle system. The principle of superposition tells us that the force on particle 1 is just the sum of the force on particle 1 because of particle 2 and the force on particle 1 because of particle 3. So if I calculate the force on particle 1 because of particle 3, get a value. Now, in this case we have vector, so I'll say A. And I calculate the force on particle 1 because of particle 2 and get a vector, say B. I can add these 2 vectors to get a vector C, and that C is the force on particle 1 because of particle 2 and particle 3. Now this is just an oversimplification of the principle of superposition, but in general what this is saying is that if I have particle 4, particle 5, particle 7, particle 6, and I have n particles, then the force on particle 1, because of all these n particles, is just the force on particle 1 because of particle 2, the force on particle 1 because of particle 3, the force on particle 1 because of particle 4, plus force on particle 1 because of particle 5, and etc. all the way to n added together. And if I do that, I can get the force on particle 1 exerted by all the other particles. And that's the principle of superposition. So, in fact, we can scratch out the n now, or scratch out the 3, and now we can add an n. So we've just made this model, or this concrete example, much more interesting to us. Because instead of just having a 2-particle system, we made it into a 3-particle system. Now with the principle of superposition, we have an n-particle system. So in fact, this condition is practically removed. So the main condition, or main limitation, is just that all particles are stationary. So now that we've talked about and discussed the principle of superposition, let's move on to the electric field. So what is the electric field? Well, the electric field is quite simple to describe, but its implications are actually way more than you can count. So let's talk about the electric field. So let's say I have a particle Q1. Now this is particle Q1. Now I can call it particle Q1, or I can just call it particle 1. Now in this case, particle 1 is going to generate the electric field. So let's say I'm considering this point in space over here. What is the force on that point? Now this may seem highly unrealistic because a point doesn't have a mass. In fact, a point is not even particularly or mathematically described precisely, because we can't write a formula for a point. We can't analyze a point deeply or mathematically, or at least with the mathematics we have right now for the purposes of this video. So what does the electric field say? Well, the electric field says that the force on any point, or on this point, is the force exerted by particle 1 on that point, assuming that there's a unit charge at that point. So in other words, if we assume a unit charge to be at this point, and then compute the force, that's the force exerted by particle 1 at this point. And we can do that for all other points. And precisely, we get an electric field defined at all of these other points. So, you can draw many more points, stuff like that. And precisely at this point, we're computing the force, assuming that there's a unit charge there, or the value of the charge is just 1 there. Now, unit charge just precisely means that we're considering the fundamental piece of charge, and we're not going to be discussing more about units in this section, but mainly what a unit charge is just saying is that assume that the charge is 1, and then a unit. Now, for our purposes in this section, we're not going to be discussing about unit. We can make a lot of other videos about that unit just itself, but we're not going to be defining or talking about the unit because that'll just make things more complicated in this video. Okay, so if we assume that there's a unit charge at this point, then we can consider the force on this point exerted by particle 1. And that's the force assigned to this point. And we can do that to all these other points and get an electric field described at every point in all of space. So that's precisely what an electric field is. Now, before I end this section, it is inevitable that I talk about this formula right here, because I've had it in the previous section as well, but not really discussed it. So, this is the formula over here. So it looks pretty daunting at first, but it's actually pretty simple. So what this formula is considering is it's considering the electric field on particle 1 because of all the other particles. And once again, we're assuming a unit charge. That's why we don't see another Q1 or another Q over there, because we're assuming that we're only considering a unit charge. So precisely, say I have particle 1 here, and I have particle 2, particle 3, particle 4, particle 5, and etc. And I want to consider the electric field at particle 1. Let's say that particle 1 is a unit charge. Well then, if it's a unit charge, then the electric field at particle 1 is just the electric field, or due to particle 2 at that point, the electric, so we'll call that value, in other words, that force, A, the electric field at that point due to particle 3, which we'll call B, and likewise C, D, etc. And we add all of these together, so A plus B plus C plus D, to get ultimately the electric field on particle 1. Since we're assuming the unit charge, that's why we don't have the other Q over there. So in essence, we're just considering the electric field on particle 1. That's just the force or the electric field on particle 1 because of particle 2, the electric field on particle 1 because of particle 3, and the electric field on particle 1 because of particle 4, and etc. And if we sum all those vectors or all those electric field constituents apart, or constituents together, we get this formula over here. Now, that's essentially the intuition behind that formula, but let's elaborate more on this itself. So the index is J. So in order to understand a summation, in this case, let's just work out the terms. So we have 1 over 4 pi epsilon naught Q1, or not Q1, let's skip Q1 because we're considering particle 1. So we'll consider Q2, R squared 1, 2, E1, 2, plus 1 over 4 pi epsilon naught Q3, R1, 3 squared, E1, 3. Now, in our previous section, we observed that R is just going to be scalar and we ignore the subscript. So the purposes of this section, just ignore the subscripts because at this point, we're not considering the distance to be a vector per se, but rather we're just considering the distance to be a scalar quantity. And we can even consider this to be the magnitude of a vector. Okay, so we have 1 over 4 pi epsilon naught Q2 over R squared 1, 2 times E1, 2. What does this look like? It looks like Coulomb's law, assuming that the other Q has a value of 1, or it's a unit charge. So this is precisely the force on particle 1 because of particle 2, assuming that there's a unit charge at particle 1. Similarly, this is the force on particle 1 because of particle 3, assuming that at particle 1 we just have a unit charge. And we can keep on going like this for how many particles that we have, and we'll get the electric field at particle 1. Why can we sum all these terms? Well, that's because of the principle of superposition. So that's, in essence, what this summation is describing. And that's what the electric field is. The electric field just describes the force on a particular point exerted by another particle. So the force on, let's say, point 1 exerted by particle 2, assuming that point 1 has a unit charge there. And we can use Coulomb's law and a variety of other things, assuming that there's unit charge and etc., to calculate the electric field at that point. So now that we've discussed that, we can make this section to an end. Thank you for watching The Dawn of Electromagnetism.